Linear algebra is the study of how dimensional space transforms. Every matrix calculation dictates a physical distortion, a stretch, a rotation, or collapse of geometry. Early coursework focuses on the mechanics of multiplying rows by columns and isolating variables across numerical grids. Advanced university exams, however, move past computation to test structural logic. At this level, the numbers often disappear entirely. You are handed abstract variables and asked to prove universal conditions. These problems require mapping the transformations of a matrix without knowing a single value inside it. To navigate this level of abstraction, we will deconstruct three specific exam typologies. We are going to reverse engineer logical proofs, stress test subspace axioms, and build direct mathematical bridges between distinct matrices. While a computer can execute matrix multiplications at scale, the advantage in STEM fields lies in proving the underlying rule sets that govern those systems before a single calculation is made. Consider the first problem typology. We must prove that if the equation a cubed times x equals 0 has infinitely many solutions, then a times x equals 0 must also have infinitely many solutions. We begin by translating the phrase infinitely many solutions into its structural meaning. If a homogeneous system has infinite solutions, it means the coefficient matrix, a cubed, lacks an inverse. By definition, a matrix without an inverse must have a determinant equal to 0. Here we apply a determinant axiom. Multiplicativity allows the exponent outside the function. The determinant of a cubed equals the determinant of a cubed. Since this cubed number equals 0, the base itself must be 0. Therefore, the determinant of matrix A is 0. We have now isolated the core property of matrix A. Because the determinant is 0, matrix A is non-invertible. And since matrix A lacks an inverse, the homogeneous system A times x equals 0 must yield infinitely many solutions. The equivalence theorem allows us to map the behavior of these systems without ever knowing a single numerical element within matrix A. Our second challenge involves testing two different subsets to determine if they function as valid subspaces. The first is set W, defined by all vectors satisfying the linear equation x plus y minus 2z equals 0. Geometrically, this equation describes a flat, infinite plane that intersects the origin point. Because it is defined by a simple first-degree linear relationship, set W passes the algebraic closure tests for both addition and scalar multiplication. It is a valid subspace. The exam introduces a different set U. This set consists of 2x2 matrices where the product of their 4 internal elements equals 0. Set U contains the 0 vector, but it must still be tested for closure under addition. To test this, we define matrices V1 and V2. Both belong to set U because their internal products equal 0. The closure axiom states adding 2 valid elements produces another valid element. We add V1 to V2, resulting in a matrix of all 1s. The product of these elements is 1. Since the product is not 0, the matrix is not in set U, and the closure axiom fails. Rigor in linear algebra requires testing bedrock axioms against specific counterexamples, rather than just relying on superficial patterns. The third typology works backward, using provided solutions to build the original matrix. We are given a 3x4 matrix in reduced row echelon form, containing unknown variables, A, B, and C. We find these variables by utilizing two fundamental column vectors representing the system's solutions. We compute the dot product of the top row and the first solution vector. Multiplying yields 2 plus A equals 0, showing A is -2. Repeating this with the second solution vector gives -4 plus B equals 0, establishing B as 4. The zeros and ones inside the solution vectors isolate specific columns, allowing us to solve for each variable independently. Fundamental solutions act as geometric constraints that dictate the exact content of the coefficient matrix. Our final challenge is to find an invertible matrix P that transforms matrix A directly into a different matrix B. The starting point is the fact that matrices A and B are row equivalent. They share a hidden architectural baseline. Two row equivalent matrices reduce to the same reduced row echelon form, which we designate as matrix R. We label the operations required to reduce matrix A as P1 and the operations to reduce matrix B as P2. This gives us two equations. P1 times A equals R, and P2 times B equals R. Because both operations yield matrix R, we can set the equations equal to each other. P1A equals P2B. To find the transformation from A to B, we isolate matrix B. Multiplying both sides by the inverse of P2 moves the transformation array to the other side. The required transformation matrix P is equal to the inverse of P2 times P1. By identifying a shared intrinsic property, we can successfully build a functional bridge between two entirely distinct datasets. We have linked infinite solutions to determinants, tested the boundaries of subspaces, and used reduced echelon forms to map different matrices to one another. Each of these proofs demonstrates how specific algebraic properties, like determinants and row equivalents, govern the behavior of unknown matrices. Navigating advanced material requires recognizing these invariant structures rather than focusing solely on raw calculation. Approaching linear algebra as a study of matrices as objects governed by strict logical rule sets provides a framework for solving complex systems. Apply this logic to your own work. Isolate the core axioms and identify the underlying properties before committing to the final calculation.